Let's look at some special forms of Brownian motions. So one particular one is Brownian motion with drift. So what you have now is that you have these random steps, but they're not centered around zero. Rather, you expect a certain average drift. You can still come down, but you expect to, on average, drift up or drift down. So one can define it as a process, a stochastic process. X of t with t greater than 0, such that, so you have to start from somewhere. So again, you can take arbitrarily that it starts at 0. And again, these has stationary and independent increments. And finally, these increments are given by the normal distribution, but this time the mean is not 0. Is normally distributed with mean you have some mean, and that mean is not 0 and it's not some constant. It increases linearly. And variance, as before, you have certain sigma square t variance. And as before, we can have, one can standardize it by taking sigma is equal to 1. So this can be thought of just like last time. This is a limit of a random walk, but with unequal probabilities for step ahead and back. So if I consider the random walk xk such that it takes values 1 and -1, and this probability is p, this probability is 1 minus p, then I can define this total displacement variable. And again, you have this step size. Where this is n, you have n steps. And again, by use of the central limit theorem, this will become a normal distribution. And the limit when n goes to infinity. But in that limit, you want something to remain constant. So essentially, again, you want that delta x, this delta x square t should go to some sigma square, this kind of a limit, as we did before. So, but what we need to see to apply this theorem is that what is the mean and what is the variance which we are getting. So the mean of this S of t is delta x times n and it is just the mean of all these variables, and the mean of these delta xi, any of them, is clearly simply p times 1 plus 1 minus p times minus 1. So it's 2p minus 1. So the mean is this, where n is p over delta t. Mean and the variance is this delta x gets squared. We have n for the n variables, and the variance of each one of them, it turns out to be equal to, using the formula for the variance, this turns out to be this one. So I have p over delta t We have to take limits so that we get some finite mean and some finite variance. So if I have to cancel these, so if I take, for example, delta t, so that these cancel, but then there's this p. So if I choose plus, why did I choose this? Because of this thing. So delta x is under root delta t. So this will give me, this will introduce a under root delta t over there. And then I see s of t, this goes to delta t goes to 0 and delta x goes to 0. This goes to, in this limit, mu t, and the variance goes to t. I haven't included a sigma square over here, just to make it a standard random walk. Otherwise, I'll have to adjust it properly. I could have done this, but this is just easier to see this way. One can easily see these things from here. So like from here, 2p minus 1 is equal to mu under delta t. So when I put it there, I get delta x t mu under root delta t over t, and I'm taking the limit, then delta x over delta t, this goes to 1. So this becomes delta x over under root delta t, t mu, and this goes to mu t. The same limit, one can see that what's happening to the variance. You have 2p minus 1 is mu square delta t. And you get this, and then you get in the limit, this goes to 1, while this goes to 0. So this becomes simply t. So you have got what it says is that if you look at one particular time, t, you have at any t, we have a normal distribution with mean mu t, controlled by what time you look at, and variance t. Now, one can, let's do some example involving this. So imagine we want to compute the probability what is the probability okay, that the Brownian motion will hit A before hitting minus B, given that A, B are some positive number. We want to compute this probability. To do this, let's do some conditioning. Let's first define P of x as the probability that at time t, we are at x, and x is something between b and a. So we are looking at this probability. It's a before minus b conditioned on that x of t is x. Now, this one, we're gonna derive a differential equation for it. For this, So what I do is I define its the change in process for a where finally I'll take h to be very small. So then I can write this probability as the average of this probability, which will encounter errors of order A. So what is this probability? This is the probability that x of t is equal to x plus x of t plus h minus x of t, which is x so this is t plus h. Uh, so this gives you, so this is essentially we are averaging over a small variation around this point x. So this gives you we use expand around x. This gives us the Taylor series. But now these is expectation is taken over the variable y. Y is the one which is the random variable now. So this just becomes p of x. Y is an increment. So by the definition of the Brownian motion, this is a uh, this is a random, this is a normal variable with mean equal to mu t. But t here is the increment size, which is h. So mu h. And this is the square of the mean, which comes out to be this. And order h. So all the other terms will have higher orders of h. So now when we take So this cancels with this, and dividing by 8 and taking limit is going to 0. This 8 goes, this 8 goes, but this brings it to 0, and there are no other terms. So we get 0 over 2. This is the differential equation which we get, and we can integrate it to get 2 mu p of x is equal to C1. We have to integrate it further. To do that, we include an integrating factor. So that this becomes a total derivative and this gives you when I integrate, I get some mu, but I can again absorb it into this constant. And I get this, so p of x, this becomes some constant, another constant, e minus 2 mu x. Now I can find these constants by applying the boundary conditions. So using the boundary conditions, that P of A is, what is P of A? P of A is the probability that at time t, which is between your some time and you, at that time you are already at x is equal to A. So which one you're gonna hit first? A or B? Obviously A, you have already hit it. So this is 1. And probability of minus B, that x is equal to it's already at minus B. So what's the probability that you will hit A first, then hitting minus B? That's 0. So putting these here, I get E minus 2 mu A, and 0 is equal to E 2 mu B. So you can solve these. Solving, one gets so if I subtract these two, I will get C2 wait Yeah. E minus 2 mu b. So C2 is 1 over this plus minus E2 mu b. And C1 turns out to be when E2 mu b over E2 mu b minus 2 mu a. So then I put those back in to compute this probability over here. And then that gives me b minus e minus 2 mu x. Now, if I start, now if I put these condition, that condition was that the Brownian particle, the Brownian process was at x of, as the Brownian condition demands that you start from 0. So we were looking at t is equal to 0 and we started at 0. So all we have to do is put x is equal to 0 here. So then this process hits A, or I should say goes up to A before going down to B is this. So this result is true even if mu is negative. So mu is the average. So mu is the parameter for drift. And it doesn't have to be positive. You could be drifting down. So Uh, so if now I can see, so suppose mu is negative. That means you start from here and you have a drift going down, and here's some minus b. Here, if you reach here, you kind of stop. You have done too bad. So you're asking the question, what's the probability that I'll reach A first before reaching minus B? So you have a drift now, but you are hoping that a random jump takes you to A. So it's that probability. And suppose mu is negative and take B to infinity. So this is then giving you this probability which we computed, all that junk here, is the probability of hitting A before hitting A ever. Because what's the alternative event? Alternative event is that you hit B first. That means you just drift off down to minus infinity. Obviously, there's a drift taking you down, so there's no guarantee that you will hit A. We're just going down. So what is that probability? Well, all we have to do is put B equal to in infinity over here. I had a small B. So I have to put B is equal to infinity over here. So when I put B equals to infinity over here, I have these two infinities, so I have to cancel that. I have this thing. The probability was E to mu B so this is equal to dividing by E2 minus B. Now as B goes to infinity, this goes to dividing by e to mu b goes to 0, and this goes to 0 as well. So the probability is 1. You are assured to reach any height above before sinking down to infinity. So you can play the waiting game and you will reach, although you have a drift down, but you are assured to come back up. Now, let's look at another example from here. This motion with the drift, you can also include the one can include uh, standard, non-standard Brownian motion. So then one can define, well, one can consider this. This is the standard Brownian. And I have created this new random variable. This is a random variable, this is a random variable. Now this is standard Brownian. That means at any t, this is normal. And by adding this, it's mu t, because the expectation of this is 0. And the variance of x hat of t, since this is not random, doesn't give you any variance, and all the variance comes from here. So it's sigma square variance of this guy, which is t. So this variable then is the general Brownian motion with a drift. Now one can consider another kind of Brownian motion, which is called the geometric Brownian motion. So what's a geometric Brownian motion? So suppose what you expect, you are considering a process, but the process is such that you do not expect equal increments at equal times. Like in the Brownian motion, what is happening is that if you take equal intervals, then you have some starting point depending on where you have reached here. You expect to make equal size jumps within a range. This is the variance using normal distribution. But you can consider some processes where it's not the jump which is equal, it's actually the percentage which is equal. So like if you are considering the stock prices, so you expect that the variations up and down will be random, and you can assume that it's you can model it using a continuous limit of a random walk process. But what you don't expect is that suppose a stock starts at a price 30, and in the beginning it's taking, people are just betting on it, and in a day you expect the price to jump up or down by 1. And then there's a drift to the process, and the stock finally reaches 500 because the company is doing well, and after some time you reach, many years, you reach the value 500. You don't expect now the jumps to be of size 1 or -1. You're describing the same stock using the same process, but you don't expect the jumps of size 1. You expect the jumps of the same percentage. So to model that kind of situation, we consider the geometric Brownian motion. So what's the geometric Brownian motion? Well, you just consider this variable, where this is Brownian, then this is called the geometric Brownian. So So what's the relation with what I said? So suppose you're considering the price of a stock or a commodity, and y of t, let's consider it in the discrete case. Y of n is the price at nth day, and y of n minus 1 is the price on the previous day. So you don't expect that y n minus y of n minus 1 are identically distributed. Rather, it's the ratios, the percentages. Should be identically distributed. And if I define a variable, like this, then the price on the nth day is the yn minus 1 is then so on, assuming that just taking y of 0 to be 1, so that means the stock price is the product of identically distributed random variables. So they become so then they are described when you take the limit y of t becomes something like that, because this has the property like this. Now you can compute the expectation value of this variable. It's just x of t. This is just the random normal. So this, if assuming that this is the standard normal, this gives us e to the t over 2 and the variance gives us ET. I can consider more general ones, so I can define y of t as x of t, where this is a general Brownian with a drift. So this is then this variable. And then when I compute this, it gives me this, and the variance gives me, using the standard formulas for the Gaussian, it gives me this. Okay, so let's consider if we model this, we use this to model stock price, then what would this mean be? Then let's compute this thing. So you start with some standard price, let's call it 1. What is the probability that after time t, you would have incurred a loss? So y of t, you want it to be less than y of 0. So that would happen if x of t and y of 0 is 1. So that would mean x of t will have to be less than 0. So that is the probability. This probability is simply saying that this cumulative probability, this is equal to this probability, and this is equal to so that means this probability will be minimized for smaller values of sigma and larger values of mu. So this mu is the drift upwards, taking mu positive. If mu is positive, it's saying that as time goes on, you have a less and less chance of incurring a loss. And the higher the drift upwards, the less chance you have. But this is the what is called the volatility. Volatility can still cause you to incur a loss, and you want less volatility to be protected against this kind of loss.